And we are recording. Um, Welcome to the evening of Python coding. Here in this meetup, we always show a demo of a library, typically open source. This time we have again Kevin Kho, who already gave us a great demo a few months ago, but now he's gonna talk about his new project, Fugue. And if anyone is interested in big data and many other capabilities, then Kevin will explain. Kevin, take it away. Tell us about Fugue.
Yeah, thank you. So, a bit about myself. I was at Prefect, which is a Python-based workflow orchestration company. Before Prefect, I was a data scientist for 4 years, and then I recently left Prefect last month to focus on Fugue, which we'll be talking about today. Questions very welcome during the presentation. I have a lot of content, but I would rather skip parts of my presentation if there are questions or discussion. Um, and feel free to just throw any questions in the chat as well. I guess the first question I have just to get, I know this is a Python meetup, so I just want to know, is there anyone, number one, is anyone unfamiliar with pandas? And number two, what's the experience, does anyone here have experience with either Spark or Dask? And that would help my presentation if you could just type it in the chat. So with that, we'll get started. I'll share my screen. And today's topic is porting existing code to distributed computing. So this is very, again, I know we're a Python meetup, so if you have any questions, just interrupt me. But this is a very data scientist focused presentation. So we'll be talking about data frames primarily, right? So the first thing, okay, so we have a couple people here. So number one is that uh, Pandas, which is the most common data science library for working with data, is known to be inefficient, right? So number one, um, Pandas creates a lot of intermediate copies of data, and so it's not memory efficient. In fact, the creator of Pandas said that in order to work with data efficiently, you need to have 5 to 10 times as much RAM as the size of your data. So if you have a 3 GB data frame, ideally would have 15 to 30 gig of RAM, right? So Pandas becomes inefficient pretty quickly. So when people run into issues like they start to experience bottlenecks or the data gets too big and the performance starts to degrade, then they look at how can we scale our code, right? And that's a very common scenario. So the most frequent thing, like talking to data practitioners, is that they will easily, like for example, they have a code running on a virtual machine that is like 16 gigs RAM, and then it starts to become slow. The most common thing that people will do is like they will bump it up to 32 gig, and then when the 32 gig starts to fail, they'll bump it up to 64 gig, right? So that's not this helps your memory problem, but it's still not efficient because pandas is designed to be single core, so there is no built-in parallelism or multi-threading or anything like that. Maurice is asking a question: what are some examples of data degradation? No, I don't mean the data degrades. I mean performance degrades. Like instead of taking an operation taking 30 minutes, it takes 1 hour, and then starts to take 1.5 hours, and then so on and so forth. Maybe it's even just hangs, right? So I'm talking about performance. There are like things start to feel sluggish, right? So with vertical scaling, you do fix that memory problem, but you don't what you don't take advantage of is normally you have 32 gigs, you have like 16 cores. Pandas will still use 1 core by default, right? So even if you increase the memory, a lot of times the CPU remains unutilized. And another problem is that yes, you can increase the memory and you can run everything on a 32 gig machine, for example, but most of the time, the you only need 32 gigs for one specific step, right? And outside of that specific step, you don't need as much memory. Evelyn, do you have a question or? Uh, okay, I'll just keep going. So a lot of time, if you have a 32 gig like machine, chances are you only need 32 gig for one small step, and the other times you don't need that much. So in effect, there's an underutilization, right? So the ideal step is like, can I use a 16 gig machine, finish that, and then use the 32 gig machine for the expensive step, and then go back down to 16, right? But the vertical scaling doesn't really give us this flexibility easily, right? So what we also see commonly is that people resort to parallelization themselves. So yes, pandas cannot natively parallelize. So what people do instead is they create many pandas threads. So if I have 4 cores in my machine or 8 cores in my machine, what I can do is I can split out my CSV file into 4 portions or 8 portions. And then what I'm going to do is create some executor and then map over those files. Now, this is not a perfect solution either, because it's number one, there's no concept of memory management, right? I'm firing off all of these processes, but they don't know about each other. So overall, it's very easy to overload the system. For example, there's this Stack Overflow post here, and basically he was trying to do the same thing with 1,000 data frames. And 1,000 data frames started to 1,000 started to overload it. So what he did was he had to chunk his mapping operation. So he has a while loop, and he processes like four what we call shards or parts of the data frame each time, because he has 4 cores. So you do that, and this becomes inconvenient for the user also, because what happens is they need to manage the memory. They need to know the limitation of the machine, but they need to explicitly manage that. Um, so the other limitation of this is, yes, this can parallelize over a single machine, but if you want to utilize a cluster, this does not extend to a cluster. So if you want to use a cluster and utilize multiple machines at the same time, that's what we call distributed computing. And distributed computing, the most common frameworks are Spark or Dask and Ray. So a lot of the times it will be more convenient to uh, use one of these instead, even on local mode, because they do have those concepts of memory management, right? They do have those optimizations built in for data operations as well. So a lot of times they can squeeze more performance out of what you're trying to do. So when do you need to reach for one of these frameworks? The Dask machine learning documentation has this really nice picture. I'm going to reduce this size a bit so it fits. So if you're in this bottom left quadrant here, where all your data still fits on the machine, and it's your your uh your program is still like taking a reasonable amount of time to execute, you are fine. You can just stick to pandas. But then either the data outgrows your machine, which is memory bound, so you need to get more memory somehow, whether that be vertical scaling or horizontal scaling, getting a cluster. Or number two, maybe your data does fit in RAM, but you're trying to train like 10 machine learning models, and each of them takes 1 hour. So your whole thing is taking 10 hours. That is what we call compute bound. So over here, what we can do is we can have 10 machines, and each of them takes one model each, and then your total pipeline is reduced to 1 hour, right? So if you're either if you're in either of these buckets, then you would need to reach for distributed computing. And these are the most three popular frameworks. So Spark, probably most popular, Dask number two, and Ray more recent. So I won't go as much into Ray unless there's questions about it specifically. But between Spark and Dask, I think the difference here is that Spark in general is very focused on the data frame abstraction, whereas Dask has a lot more primitives towards like for example, they have like Dask array, Dask bag, which is like JSON. So the types in Dask are more flexible, whereas Spark is more about the data frame. But because Spark is committed to that data frame abstraction, it tends to be able to optimize operations more. So it may be more performant, whereas Dask is more flexible, but then you lose that, like, because there's a lot more stuff you can do, it can't optimize as much. Spark, of course, if you're not familiar, is also built on top of on Java, on the JVM. And so it's built on Scala, which runs on the JVM, the Java Virtual Machine. Dask is built on top of Python libraries. So Dask is pure Python. You don't need extra dependencies. it's a lot easier to install, manage. But so yeah, that's the trade-off between these two. Are there any questions? I've been talking for a while, just checking if there's any questions. Okay, if there's none, we'll keep going. So
You're doing great, but I want to add one more thing. You said you worked in Prefect, so tell a bit more about Prefect. It's also one of those mechanisms.
yeah. So Prefect is I worked at Prefect my last job, and Prefect is a workflow orchestrator. So if you have a bunch of scripts that you're trying to connect together that runs on a schedule, Prefect is something that can manage that and the dependencies of those. Now, thank you for the link, David. Now, with Prefect was because of Prefect was designed for data scientists or people on the PyData stack. So because of that, it had Dask as a native integration. So Prefect combined, and if you had like hundreds of tasks or thousands of tasks, it would submit it to Dask to execute. The question here is, will I be sharing this notebook on GitHub? I will just give you the link right now because it's already up there. Real quick.
Yeah, if you look at the meetup page, it's already published there.
I changed the link actually. So yeah, this is updated. So the notebook is there. So going back to distributed computing, this is an image taken from the Dask, one of the Dask issues on their GitHub repo. Basically, the typical architecture is that you have what you call a client, and could be my machine or like a Python script or a Jupyter notebook, and then I'm connected to the cluster somehow, and I am sending commands to the cluster, and the cluster is composed of schedulers and workers. So the scheduler is the one that's responsible for saying, hey, I see worker 3 is underutilized. I'm going to get this next task and pass it to worker 3. Or worker 1 finished this thing, so it's going to collect that. So when we deal with distributed computing, it's the scheduler orchestrating all the work that happens on the workers, and they send the results back to the scheduler, and it could just send the result back to the client. The second thing we need to talk about is partitions. So when we talk about a Dask data frame, we said that Dask is built on top of pandas. So what you'll find is that one Dask data frame is the collection of pandas data frames. So for example, if we have data over a year, that's really large. You could split it by month. You could partition it by month. And this could be your January data, your February data, your March data, etc. And each of these will live, for example, one box like this will live on one worker. And then same thing, like this box is this partition will live on this other worker, and so on. So these partitions are now split across the cluster workers. So just a quick this link here is a very good blog on partitions, and we this is just some intro to partitioning that will help us build a better intuition for distributed computing. So first, when we talk about the ideal partitioning strategy, if your data set is this rectangle, ideally you want even partitions. So here we have like 3 partitions, and this executor 1 holds 1 partition, executor 2 holds 1 partition. So again, going back to the analogy of having, like, let's say a data frame of activity over time. This could be the January data in executor 1. This could be the February data in executor 2. This could be the March data in executor 3. And this is the ideal partitioning strategy. If you have a scenario where the partitions are skewed, what this means is that a certain month would hold more data, for example. So here, January obviously holds more data compared to these two, like February and March. Now, this is sometimes unavoidable, but maybe you can think about how you can repartition your data better so that you can have a more even distribution. And the reason that you want an even distribution is because look over here, executor 1 contains 2 partitions and executor 2 contains 1 partition. So what happens is if I do some data frame operation, executor 1 is my blocker, or is the limiting factor here. So executor 1 will take twice the amount of time as executor 2, And during this time, executor 2 doesn't have anything to do because it's just waiting for executor 1 to finish. So ideally, what you want to do is to have this even partitions so that your execution time is kind of uniform throughout your executors. And that will be the optimal partitioning strategy. The other thing that we need to talk about with partitions is shuffling. So over here, let's assume that they are partitioned by month. There are some operations where we need to shuffle data around between the workers. And then we need to, maybe we're performing an operation by, instead of month, we're doing like by company, or we're doing by some other split. In that case, we need a shuffle, which is a movement of data between the executors. And then this movement of data, after that, we can perform other operations that require this partitioning strategy. But the problem here is that this is an expensive operation. It's unavoidable, but it is an expensive operation, right? So a lot of times we are waiting for the shuffle is like a huge cost to distributed computing, and sometimes we can avoid it if we're just a bit more if we just pay more attention to it. So with that, let's get started to coding demo. So here we're gonna compare Panda, Spark, and Dask, and just get a minimal like hello world to each so that you can see the differences in syntax. Over here, I'm going to create a data frame called, I think I can run this. It may take some time because Spark, again, you have to make that Spark section. So this will take some time, but I'm making a pandas data frame over here. There's 3 rows, and pay attention to this value column that is A, B, and C. So I'll just show it here. So we have this A, B, and C, and what I want to do is for letter A, I want to replace it with apple. I want to replace B with banana, etc. So how do we do this operation in pandas? There is a built-in function method called map, and all we have to do is say map and pass in that dictionary. So this is fixed. This already works. For Spark though, it's not as simple. We need to create this map, and then we need to. You don't really need to like understand everything here, but then this is I really just got this from Stack Overflow. But basically, you have to create the map and pass that to the mapping expression. Pass this mapping expression and pass the item in that column, right? So same thing here, we get the same result. The point is that there's just some syntax difference with Spark, and this isn't this is not an isolated case. For a lot of operations, we'll see different syntax on how to do it. For Dask, it's very similar to Pandas because Dask again tries to be like built on top of the Pandas API. So it tries to have some parity. So now for Dask, you'll see that I'll take this out first. It's just this operation, but it gives us this weird thing. That's because Dask evaluates lazily. So it builds a graph of all your operations first. And when you actually need the result, you call .compute. And this is when it triggers everything to be run. So that's when we call .compute, we get this data frame back. Now let's take a look at the second operation. We want to use the pandas apply column-wise. So again, I make my 3 data frames, pandas, Spark, and Dask. And this is my function. So for every column that in my pandas data frame, I want to apply this simple x plus 3. So I'm going to run this function. And then the same thing, I'm going to call df.apply, pass this function, and this just adds everything. So this is pretty standard. For Spark though, it's not as straightforward. I have to create a UDF, and a UDF is applied per row of my data frame. And then I have to apply the UDF on each column. Now let's look at Dask. And for Dask, what I want to focus on is this API parity here. So I will run this command, and you're gonna see an error. So we use the apply. It has an apply, but the error is that the apply only supports row-wise, and it doesn't support column-wise operations. So why does Dask not support column-wise operations? Anyone can take a guess. I'll give like 5 seconds. if anyone. Why does Dask prevent column-wise operations?
I
Okay,
would
I'll just
guess. I would
yeah,
guess. I
sure.
would guess.
Yeah.
So because it has to apply them on multiple machines, and like it's more complicated, then you has to synchronize between those.
Yes, yes, in a way. But so when you do apply, this function is a black box, and that doesn't know what this function is, right? But what if I tried to do something like this? Like I tried to get the range. I'll make this bigger. Oops, yeah, there. What if I tried to do something like this instead, right? The problem is that when we talk about our DAS data frame or distributed data frame, it's partitioned by pandas data frames, and then this function will run on each pandas data frame, right? So DAS prevents this because if you do, depending on the function that you're giving, if you do it column wise like this, and you're expecting the maximum in the column and the minimum in the column to be used, you're going to run into inconsistent results because this is applied on like January data separately, February data separately, March data separately, right? Because partitions are a row-wise thing, not column-wise. So you can't use apply on a column. So any questions there? And if not, we'll just keep going here.
What if your data sets change from, as your example, January, February, March? What if your data, your schema, the back end changes? How does that change how you query your data here?
Is your question how okay, is your question like, for example, January, February, March? So like January is like one partition, February is one partition, and March is one partition. And is the question like what happens if my partition is based on something different? Like what if
Yes.
it's by
Yes.
company, right? Regardless of what your partitioning strategy is, you have partitions and your data is split in some way to be able to parallelize, right? So we split the data, we parallelize the operation, and then we re-aggregate it. So regardless of what your strategy is for splitting the data, the fact that the data is split is the one that requires more nuance to handle. Makes certain operations that we're used to on one machine, makes them incompatible, right, with the distributed setting, because the data is split, right? Does that answer you? I hope so.
Yes. Yeah. Thank you.
Okay.
Appreciate it.
So I mean, let's say I indeed was able to. Oh, I think there's a question. Yes. Nicole, did you have a question? Okay, if there's no questions, we'll go on. So let's say we're able to actually, like I had a pandas job. It was becoming sluggish, and I was able to translate all of my code. I did all the work, and I brought it to Spark. Even if I can figure out the syntax portion of it, there's actually behavior issues as well that are inconsistent between these frameworks, right? So over here, I'm just going to make a new data frame. Note that there is a none value here, and this is where a lot of the inconsistencies happen. So my first operation with pandas, I'm going to do group by on column 1, get the mean of column 2. So you're going to see that the null value here was dropped, right? Now on Dask, it's going to be the same. The null value is dropped. But on Spark, what you're going to see is the null remains. So Spark keeps the null, Pandas drops the null. So there's some inconsistency there. In order to get them to be consistent, there's this drop NA flag that you can pass in to Pandas, and now you can retain that null value. So we need to still be aware of these inconsistencies. Now the second one I'm going to show is sorting. What if I sort this data frame? You're gonna see none at the bottom here. Now if I bring it to Dask and first of all, I can't even bring this to Dask. This is the error message. This is because Dask does not support sorting by 2 columns. They only support sorting by 1 column. And the reason for this is that in general, sorting over a data frame that is like pieced together, that is distributed across multiple machines is very expensive. You have a lot of data moving back and forth, and it takes a lot of overhead to perform a sort operation to get everything globally ordered. So that actually prevents this. But we can do it in Spark. And I'm going to run this in Spark. You're going to see that David, thank you for the link. We will talk about Modin. So about Spark. You're going to see that the value was this null is first. Remember, in Pandas, the null was at the bottom, and in Spark, the null was at the top. How do I bring this null to the bottom? Well, I can pass ascending equals false, but it's not quite consistent also, because null is at the bottom, but notice B was at the top and then A was here, whereas in Pandas, A was first and B was second. So this is ascending, and it sticks null at the bottom, whereas in Spark, it is this is descent. Null actually has a value, and it is the smallest value, right? So if you're in a string, it's whatever your column is, null is actually treated as the smallest value. In Pandas, they have this thing called NA position. So they sort everything ascending or descending, and then they stick the nulls either at the bottom or at the top, depending what you prefer. So this is actually not even the same system. Right here, this is because Spark relies on Java, and null is actually the smallest value there. Whereas here in Python or in Pandas, it's not. Right. So, any questions on the inconsistencies? These are just a couple of examples. Okay, if there's none, we'll just keep going.
I have a question. You're leading somewhere with this. You're keeping us in suspense.
Oh, okay. We don't take it that way. There's just we're just getting intuition for the differences of these systems, and then we'll talk about, okay, now I have to port Python code or port Spark code, port Pandas code to Dash or Spark. How do I do that? And then what are the things I need to watch out for, right? When I actually do that. Yeah.
So you're showing us all the pitfalls before you actually show us how to solve things. Good.
Exactly. Yeah. So that when we go there, we'll know, okay, what should I expect, right?
Okay. So now the movie is not as suspenseful as before. But
no,
okay.
No. It's not like that. Now, there's other pitfalls when it comes to distributed computing. The first one is about lineage, right? So over here, I have a function that generates a data frame. It generates a data frame, but then for every row in the data frame, we sleep. This is just the sleep function of Python. We sleep for 3 seconds. So here, if I have a sorry, I'm not generating the data frame. I'm just generating a column. So here I start out with a data frame of 8 rows. So if I call this, it will take 24 seconds to run. So this will actually take some time. There's no magic here. And then we'll look at the result. Maybe I should just explain the next. So the next cell, what we're going to do is that for that same data frame with 8 rows, what we want to do instead is to partition it. Okay, so here we see the result. It's pretty expected. It took 24 seconds. I printed result and the first 3, and they're consistent here, right? There's no problem. Now for Dask, I'm going to split this Pandas data frame into 4 partitions. So we have 2 rows for every partition. And now it should take 6 seconds to perform this operation. But we're going to see it doesn't perform in 6 seconds. So here it actually took 12 seconds. Does anyone want to guess why?
The parallelization stuff always takes. It's like you always have to do extra on top of whatever you're doing.
Oh no. That's very pessimistic. No.
No,
It's not like that.
I've been parallelizing for a while. The parallelization, it's a good promise, but it works only in big numbers.
No, the issue here is that The issue here is that result over here is actually computed twice. So when we do this, it's computed one time, and then the sleep triggers, and then the second time, this is also run again. This is, whereas in pandas, they are the same. Like it runs this, and then okay, we get the first 3 rows. In Dask, this is actually runs first, and it's rerun again when we call this. And in order to prove that, in order to prove that, I can just show that the head here is different from the first 2 rows here. So it was because we used a random generator here. So the random generation was run twice. The reason for this is because Dask, when we, for example, when we do something like this, this did not run yet. This map partitions operation did not run yet. So that's lazy evaluation, right? But if we want to actually run it, we call .compute. And then .head is also another way to trigger execution. It's an action. But Dask does not know that this is going to be reused again. So after it runs it, it forgets about result. And then it will, and then you need to rerun result. Over here, result is rerun again. And that's why we run into that situation. So how do we fix that? There's this concept called persist. I guess over here, I need to persist this result. And then now this will run in 6 seconds. Result will be computed once. Persist will say, hey, keep this in memory. And then now you get that consistency. And then now it's 6 seconds. So a lot of people don't who try to bring their code to Dask or Spark, very common mistake to not explicitly persist things. The comments or okay. The second thing I'll talk about is the schema inference. So a lot of times with pandas, we're very used to just inferring schema, but when it's done over multiple machines, what happens if schema is inferred inconsistently, or in more generally, schema inference is just very expensive to begin with. So a lot of the distributed data,
Kevin, before you run away, explain schema. We have some beginners always in this meetup. So
okay.
Explain schema and explain inference.
Yeah, maybe I can just do, hopefully, let's see if I have df, and then I can just do like df.p types. This is my schema. So column 1 is of type object, which is very vague, and column 2 is of type int64. So schema is just like for the underlying system to know this is an integer or this is a string. So schema is a requirement for distributed systems. Chris, do you have a comment, question? No, okay. So here we have this we create a data frame and we have this function called add call. It's going to create a non-value in our column. So we can group by A and apply this add column. And what we're gonna find is that one row here is none. So this is pandas. There's no problem. But the important thing is that if we didn't have this none, this would be an integer column, right? But because we have none, integers cannot hold none. So now it becomes type object. This actually becomes type object. But how does that translate to Dask? So here we try something. We create a pandas data frame. We create a Dask data frame from pandas data frame, and we apply the same thing again. And what we're going to find is that it actually, even though pandas knows it's going to be object, Dask is kind of confused and it just infers, but it inferred incorrectly here. Before I go on, David has a question. What is this? Okay, so David's comment is about why the project is named Fugue. Han, the Fugue author here, is actually in the chat. I don't know if he wants to chime in what the meaning of fugue is, but he is a musician and fugue is a music term. So Han, if you're out there, David is asking why this project is named Fugue. So let's go on. So here we do the same operation, but we have a sleep inside. And I'm doing a group by apply on the Dask data frame, and just to get the D types, just to get the output types of this operation, it actually takes 5 seconds. So it ran the whole thing. Why? Because in order for Dask to infer the types, it actually has to run your operation. And it will replace all your numeric values with 1 and all your string values with foo, and then it will run your function, and then it will see the output operations, right? So just to get the D types, all of a sudden I have to run through this. And this is also true when you actually run the operation. So here I'm running it. At call 2, we'll sleep for 5 seconds over here. But instead of just taking 5 seconds, this whole thing took 10 seconds. Because number 1, it ran to infer the schema. It ran once, and that's 5 seconds. And then it ran to actually perform the operation. And then that's why it takes 10 seconds. And then we compute, right? So how do you actually get past this? You look at the warning message. It says supply the schema explicitly. And then you'll be able to, it will be, apply the schema explicitly, and then there's no need for inference anymore. And you won't run into this issue of like duplicated execution. So David posted a link about Modin. And so when we talk about porting Python and Pandas code now to Spark or Dask, these are two frameworks that get brought up a lot, Koalas and Modin. So Koalas is basically saying, hey, change your import pandas as PD. Just change it as, maybe I'll just type it. Instead of import pandas as PD, or no. Sorry, Modin has a better example here in their documentation. And they say instead of import pandas as PD, you just say import modin.pandas as PD. And now we can parallelize everything, right? So that's Modin's promise. And Koalas is the same thing, except Koalas brings your work to Spark, Modin brings it to Ray or Dask. Ray is the default, Dask is the second. So these guys just say, just change the import, and we'll just, kind of like, I won't say hijack, but we'll just try to use that same pandas interface, except we parallelize all the operations. And I'll go into this briefly. So there are a few differences though, if like between these, like, hey, let's just change the import and pandas, right? So we can bring pandas code over to Dask, over to Spark, but there's actually inconsistency when we do that also. So this was the topic of our PyCon presentation. And what we did was we ran benchmarks, we did some experiments with Modin, Koalas, and Dask, and we kind of compared how they differ from each other. Now, I will skip a bunch of these. So here's the first one. Remember I talked about shuffle. And shuffle is when your data is spread across a couple of machines and they need to exchange data around to perform an operation. So this is my starting data. I just have like one column is a color. This is a like a mode of transportation, and then I have a random number and an integer. You don't have to worry too much about the data frame. Just know that over here I have two operations that are so I have two operations that are the same. They are just expressed differently. Let's say for each row, for each what I want to do is I want to get the maximum C value for a given for a given operation. So here I am sorting the data frame, and then I am dropping the duplicates and keeping the last value. Over here in case 2, I am doing a group by on D instead and getting the maximum index for C, and then I do a join back, right? So over here, I'm getting the highest value of C for a given D, but I'm sorting first. And remember, we talked about sorting being expensive in a distributed system. So here I have to sort, and then I drop. Here I just shuffle and self-join. And let's take a look at the performance of these two cases. So case 1, don't compare across rows. We only compare so if in case For example, pandas case 1, we just label it as 1. This means that it took 44% more time to execute this operation. So for Spark, Modin, and Ray, the second case is actually significantly faster. You can see we got tremendous speed up by reframing our logic and avoiding that sort. Whereas in pandas, because if we use the pandas method and we actually sort, these guys will sort and it will become slower. So the first thing is that even if you can just change the import and bring your code over, you're gonna find that a lot of times it's like the faster way in pandas is the slower way in the distributed system. So you can improve your performance if you're more mindful about the operations that you need to that need to be rewritten to take advantage of the distributed system better. The second example I'll show over here is what we hinted at a while ago with eager versus lazy evaluation. So in pandas, if I perform an operation, it's executed immediately. And then I showed you earlier with Dask, it's like, oh, let's construct the graph first, let's optimize it. Now it's needed, let's actually trigger it. So here we have two seemingly similar operations. There's a data frame with 100 columns. In the first one, we read the data frame and we get the minimum of all 100 columns. In case 2, we read all 100 columns, but we only get the minimum of 2 columns. So case 1, 100 columns, case 2, 2 columns. Now, what we'll see is that for case 1 in pandas, it's roughly the same as case 2, within the same ballpark. And here's where things get interesting. For Spark and for this is koalas, remember. For koalas and Dask, it actually is significantly faster. Why is that? Because in pandas, this is executed first. It's eager. So let's load in all the data. All the data gets loaded in. And then afterwards, we perform this min operation. But over here also, even in the second case, we're reading all the data again. Even though we only need the minimum of 2 columns, pandas doesn't know that. It will perform the read first, and then it will perform the subset, and then it will perform the min. Whereas over here, this is treated like a chain of operations. And because it's a chain, we can optimize it, and we know, hey, we only need 2 columns at the end. This read will only read 2 columns to begin with. So even if we have 2, like Modin, it's interesting because we have Modin, which is pandas like for Dask or for Ray, here Ray specifically. And then we have Spark, which is pandas, koalas, which is pandas like for Spark. They actually behave differently also. Modin executes eagerly. Koalas evaluates lazily. And then now for part 2, this is related to the persist that I showed you earlier. In this case, we're reading in the parquet and we're getting the minimum for these 2 columns. In case 2, we're getting the min, the max, and the mean. So over here in pandas and Modin, it's really trivial because sub is already loaded in, and then you get the max and the mean, no problem. It just adds a bit of time. With Spark or Dask, it takes a lot more time. Why? Because again, this is evaluated lazily, so sub is actually recomputed for each of these, as I showed earlier, because we didn't persist.
What are you comparing to here? Because everyone takes more time. Like, what are you comparing to the?
Oh, sorry. So, okay, let me rephrase. So pandas, case 1, we will always say it's a 1. We will fill this column with 1. And then case 2 is evaluated in relation to case 1, right? So over here, if this took 10 seconds, this means that 1.2 would say that this thing took 10 times 1.12 seconds, right? So what we're seeing is that for Spark and Dask, they actually take longer to perform case 2 in relation to pandas and Modin. And this goes with lazy evaluation versus eager evaluation. So pandas and Modin, again, are eager. Spark and Dask are lazy. So in order to really be mindful of like for Spark and Dask, you explicitly need to persist this operation so that sub is held in memory so that this will be faster. So even if you can just drop in replace, you'll still have a lot of problems of like duplicate recomputation and stuff like that if you're not aware of what's actually happening. And the last thing I want to show about Dask, about Koalas and Modin is I will just show this operation over here. So here I'm just creating a, here I'm creating a pandas data frame, and column 1 will be, I'll just run this first. So column 1 is from 0 to 9999, and column 2 is from 0 to 9999. And what we're going to do is to apply this min-max function called xmax minus xmin, which I kind of hinted at earlier when I talked about applying on the column. So on pandas, df.apply per column, no problem. We get 9999 for each, 9999 minus 0. But what happens when we bring it to koalas or PySpark pandas, which is it was renamed, and we're going to apply this min-max? What happens? Let's take a look. It gave us this instead. Why is this inconsistent with what pandas gave us? Remember earlier we talked about partitions, and this is applied on a per partition basis. So this looks like there's like 1,023 items in each partition, and then it was partitioned like there's one actually that has two, like double the size. There's an uneven partition here, but in general, when we do like this is an example of like, yes, you can just change the import, but ultimately you may find that there are inconsistent behaviors that in this case would even be silent that you would not even be aware of. So just changing the import is not necessarily like feasible. Like this is not the fault of koalas. It just has to do with the Spark engine. And this is a limitation that they face when they're trying to design a way to get pandas code running on Spark, right? So there are inconsistencies. For Modin, what happens if we run it? Import modin.pandas. Modin actually gets it right, but we'll talk about how. So Modin got it right. It was able to. But let's take a look at this this warning here. This one. Distributing pandas object. This may take some time. What is this referring to? So for Modin, if there's an operation that it can perform, if this is your distributed data frame, it pushes it back out to pandas, performs the operation, and then puts it back out in the distributed form. So obviously this adds a lot of overhead also. So you just need to be very mindful of like what's actually happening, because in this case, it may actually be worse performance to actually, or in this case, it may actually crash your program if all your data doesn't fit on a single machine. And that's where we come to Fugue. So before there, any questions? Last like 5 minutes of the presentation.
We have to have a drum roll or something. Ta-da! You know.
Tada, tada. So this is what I've been working on with Han, and Fugue aims to bring Python and Pandas code to Spark or Dask, but we do it in a way that's more mindful of how the distributed system operates. We're more explicit, yet still minimal and simple for the users. So let's start with our first example, this mapping. And we have this map letter to what you saw previously was just this code over here like this, and we just had mapdict. This was how we did it in pandas. We bring that now inside the function, and by bringing it inside the function, we can run it here. I'll just run it like this first on Fugue, and now it works. And what is this Fugue transform function doing? So number one is just the first argument is the data frame that you want to run the operation on. The second one is the function that you're using. The third one is the schema. So we mentioned that schema is a requirement for distributed systems. And then the last one is this parameter where we pass in the dictionary. This is the parameter that goes into here. And just by bringing it to transform, we can now run it on So by bringing it to transform, first we can test locally by just running this, and then now we want to run it with the Dask. All we have to say is engine equals Dask, and what I will do to show you that this is a Dask data frame that's being returned is I will print the type of this, and then I will do rest.compute. Oh, okay. I think it will still run. So here, this is just because I already have a Dask instance running. So here we were able to bring this to Dask, right? Just by specifying run this on the Dask engine. And similarly, we can pass our Spark session instead over here. And now this will run it on Spark. Spark doesn't have .compute, it has .show instead. So I just have to change this. And now we have a Spark data frame returned. And this is now running on Spark. So we have the transform function. And just by bringing it into this function, we can use that now on top of Spark, Pandas, or Dask with the same interface. The next thing I'll show is that this is the equivalent of the transform, one of the equivalents of the transform function to bring code to, like you already have Pandas code and you want to run it on Spark. We won't dive into it, but basically Spark exposes map in Pandas and it has certain requirements. So you have to like have a function with iterator PD data frame. So Fugue does this for you under the hood, handles the schema, and then does something like this. Like there's a couple things Fugue can do, but this is like one of the potential ways to get equivalent. So Fugue does it in significantly less code just by using this transform function. The next thing I'm going to show is that Fugue, we can actually, so we were able to bring this function here to Spark or Dask without even coding anything that has to do with Spark or anything that has to do with Dask. We can actually remove Pandas also as a dependency. So look at these three alternative definitions. These are pure native Python, and they are just different ways to express this logic over here. Fugue will read the type annotations over here and figure out how to perform the conversion per partition. And then it will read the output annotation. And this tells Fugue also how to bring it back out to like a Spark data frame or a Dask data frame. So we have all of these two specifically. There's no Pandas, there's no Spark, there's no Dask, pure native Python. And we can run it on the transform function as well. So over here, first we can test again locally. I'm going to use map letter to food 2. All of these will work. Oh, there's no there. So this will work. And then now because we're able to test it locally, I can now bring it to Spark or I can bring it to Dask. So I can say engine is Spark, and then we can do rest.show, and this will work. Right. So even this code without Pandas, we're able to bring to Dask or we're able to bring to Spark. And it's very explicit. It all happens in the transform function. The logic is specified here, pure logic. There's no execution code happening here. All the execution is embedded in this transform function. And the last thing I'll show before we can talk, before like just open talk, is we have this Fugue SQL as well. So over here, I have to run a couple of cells up here. So I'm just creating some 2 machine learning models, and then I'm going to apply them on this data frame. So this is what I would, this is the function to encapsulate my logic. Don't worry too much about it. The point is I just want to show, so this is how I would call it. I just want to show the SQL interface to Fugue as well. We also have a SQL interface over here that runs on Pandas, Spark, and Dask as well. So over here, I can just say,
can you make it slower? Come back and do all of the slower. We're not like time is not the thing that constrained us. Go on.
Okay.
The SQL part is interesting.
Okay. No. I mean, okay. So what we'll do is over here. I will just say this data frame is in pandas right now, and I can say select star from input data frame print. So we have a Fugue SQL interface as well. And if you want to just use this on Spark or DAS, you can just say Fugue SQL Spark, and this will now run on Spark. And then same thing, you can say run this on DAS. And this is ANSI SQL compliant. So you can do over here, you can do your select star. Maybe you can say where group equals A and print. I'll just use the native engine. So we have, this is SQL that's running on top of data frames. And Fugue SQL is its own topic in itself. So this is just a very quick preview. But what I want to show is that you can invoke Python code using the transform function. So over here, we're going to just get everything from the input data frame, transform, pre-partition, let's just say transform using predict to make it simple. And
so you're using a Python function within SQL.
Yes, yes.
And Fugue allows it.
Yes. So here, I'll just do this. So this is the Python function, and this is applying a model, a scikit-learn model prediction to create a new column. So this is the function that I'm using inside here. Right. And and I make this new column called predicted. So if I remove this just to show this column did not exist, and now we can say transform using predict, and we use this function. And same thing, we can run this on Spark. And this is a Spark data frame that will be returned this similar to the transform function. And then same thing, we can do that.
So the transform is the keyword that you added? I don't recall if it's a SQL. Okay, so
no. Yes, transform is a Fugue SQL specific keyword, and print is also a Fugue specific keyword, Fugue SQL specific keyword.
Okay, so you're using ANSI SQL, but you added the function predict, and this is a function that it's a Python function, and Fugues allows you to actually infuse those two.
Yes, and there's also added keywords. Like for example, what I can do here is, let's say input the. I just want to make sure. Okay, let's say I do something like to parquet like this, and I say this will live in temp test.parquet. What I can do in the next cell is I can actually do something like load, and then I pass this in. And I can say df is this. And then we can call star from df. Print. So we actually added keywords as well so that you can like load and save. So if we filter this and we say like where group equals A, and then we want to save this, save, and I think we should save overwrite, and then we can say test2. And then now I can do pd.readparquet, and I should be able to just get this file that I just made.
Okay, this is now I understand. So basically, you modified the SQL with your own, but you stay ANSI SQL, but you modify it to allow infusing Python and your own commands.
Yes, and this goes push down. So this will this will run on pandas. If you're running on DAS, this will use the DAS engine. Yeah, what Han said, we don't modify. ANSI SQL will always work. We just add additional syntax. We only add CTE, whatever, it all works. We just want to simplify this for users.
Well, this is very nice. So basically, Fugue allows you to actually parallelize things that were not parallelizable before, even in SQL.
Yes, because like I mean, Spark has Spark SQL, DAS has DAS SQL, which we collaborate with. It depends how your data is stored. If your data is in a flat file, now you can use Fugue to parallelize like operations on a flat file using the Python engines.
Perfect. This is very powerful. At least to me, it seems. I can only see many applications. And this will parallelize also on one machine, on a cloud, on
Whatever cluster you have.
so you can actually
Yeah.
parallelize it in a big cluster if you want.
Yes. Yes. It
Perfect.
through Spark or through Dask. Yes. This gets interpreted to Python code, and then it's executed as Python code, push down.
Okay. Now I have a trick question for you. And by the way, I understand that your demo is over and it's time for questions, correct?
Yes. Yes. Yes.
Good. So first of all, thank you for a wonderful demo. It's really amazing, all the stuff, and you prepared us to understand why we need Fugue at all. So it's like now all of those examples, now we understand why you need to switch between those. So this is perfect. But now I have a trick question for you. It's kind of a trick question, but not really. It's like it looks at the future. So you show this example, what happens, sometimes Dask works better, sometimes Spark works better, sometimes Modin works better. You show the sorts of examples of what something works better for some commands. And this is do you plan sometime in the future for Fugue to actually go ahead and analyze whatever you're doing and actually tell you, oh, it will be better with this and use it with the better engine?
Yeah. So there's a clarification there. Like, yes, Fugue is like an agnostic abstraction layer. Run this whole thing on Spark, run this whole thing on Dask. And certain things may be faster on Spark or certain things may be faster on Dask, but that doesn't matter. We don't like advocate for like, hey, this is the fastest, you should do this. Normally, if you work for a company, you have a Spark cluster. Normally, you work for a company, you have a Dask cluster already. What we just want to do is to make that easier to use, right? So we're not trying to compete against like Spark versus Dask or something. What Fugue is just trying to do is how do we provide a very minimal interface for users in this transform function?
I understand the part of standardization. So the standardization is very important, and you explain why it's important, because basically it allows you to use whatever you want and just use the same code and it will work. This is perfect. But from what you showed us before, I see that there is another level on top of what you're doing. And the level is, we not only will allow you to work on each one of them. Let's say you have something that analyzes whatever you're doing and this tells you, oh, you can do it better and uses the better engine if you have more multiple. Does it make sense?
No, that certainly makes sense. You're like, yeah. So you're suggesting like we can make recommendations eventually based on what we see from users, right?
Initially recommendations, but later on it can be automated.
Yes, I think for us, we like that may be in the form of a paid service eventually, but we're not thinking so heavily about like that may be like the product, but we're not thinking heavily about it right now. We're just thinking about the pure open source adoption. Yeah.
Okay, so first of all, thank you. So you are kind of leaning to, not leaning, but like you are kind of like looking at it. Let's say it like that.
It's
like
an idea
with
to be
one
considered.
eye.
Yes, it's an idea that can be considered. Yes.
Yeah. Okay. So this is perfect. I love it. The floor is open for questions. Everyone who was quiet, don't fear. Kevin doesn't bite. He's nice. You can come back and ask questions, and if you misunderstood something, he'll repeat it. And please come in and ask. There's a lot here, but I see the value easily. I hope some of you do as well. Come on, everyone's quiet all of a sudden. I think you overwhelmed them.
Okay.
So how long
yeah. How long what?
How long has been working on this Fugue?
Fugue has been open source for around 2 years now. And Han is I mean like we published a blog article about how Lyft specifically uses Fugue. So Han works for Lyft, and it's widely adopted there already. We have a couple adopters as well outside of Lyft, but it's been 2 years, and I recently quit Prefect to like go full time on it. Oh yeah, Han posted the link to the GitHub repo. we would appreciate if you started. Definitely something we're trying to increase. Thank you.
Okay, we will do. Kevin, while we're waiting, can you post? You can stop sharing the screen if you want, but can you post the a link to the demo you just showed wherever it is on GitHub so people will know, and I will copy it as well because I have the
Yes.
old link, unless it's the same link and you just updated it.
No. I changed the link.
Okay.
Over here. Yep. Because I annotated it a bit more so people could revisit it as well.
Okay. So here's the link for demo. Anyone who wants to. So I'm still waiting for questions. I can always ask questions, but I want people to kind of like partake in those questions because you showed very important stuff. So maybe it's still sinking in. I may ask one more question, but I do want people jump in. Some of you asked you in the middle, and I'm looking at the chat to see if anyone has asked someone in the middle that we missed.
Oh yeah. I need to scroll up as well, but Han is asking. Hannes has been answering.
Okay, so people were getting your answers while we were recording.
Yeah.
See,
Oh, and
David.
yeah. If anyone wants to reach out, like you don't want to chat here, you just want to reach out after, feel free to just add me on LinkedIn. I'll post my LinkedIn as well if anyone wants to connect and chat there as well. Although I mean, you're welcome to speak here also.
Okay, I don't see any big question coming out. So I'll ask you, how did the SQL
I have one question.
came in? Here.
Oh.
Here, sir.
So this is more of a really from PDF. I'm trying to get like the code, sample codes into my Jupyter notebook, and when you do that, right, like you don't always get all the characters. So can you see my screen?
Yes.
Do you see
I
the
can.
PDF?
Yes.
Okay, so this is just an example. So I'm like taking this PDF file, code from the PDF file, and trying to put it in my Jupyter notebook. But then I miss like some of the spacing. So what do you guys? I mean, this is just a small one, so I can just put like spaces manually. But if I'm trying to run code from which has like hundreds of lines, is there any tools that you usually use, or any escape characters that I can look from the Unicode to this should be a fairly common issue for most beginners, I guess. So I thought I would
Kirsch,
bring this up.
I'm asking for questions related to the demo itself. So
Okay. Sorry then.
wait with this after we stop the recording, and we'll come back to this. Okay.
Okay. Sure.
So if it's okay, unshare your screen, and we'll be with you in a minute. I want to make sure that we finished all the questions that are related to the demo itself. We'll be there with you in a minute.
How much of the SQL parsing and processing was written just for this, or did it come from some other SQL engine?
Yeah. So okay, we have our own parser in the project based on Antler, but it's heavily influenced by Spark SQL. But we have to add additional keywords to that to achieve what we want. Specifically, it's interesting. So the reason I didn't present a lot of the SQL portion here is just because this is a Python meetup, and heavy Python/pandas people tend to hate SQL in a very strong way. So we're just showing a brief thing. But what we want to do is we
gotta
want
have SQL.
I love it.
Yeah.
Great tool.
People are very polarized about this, but what we want to do is we want to elevate SQL as a first-class citizen, right? So currently, if you use SQL inside Spark, it's going to be Spark code, SQL code, Spark code again, right? And
Right,
SQL
right.
code is sandwiched as a second-class citizen. But on the fugue level, what we want to do, I showed an example here of like SQL invoking Python code. So we want SQL to be the dominant grammar, and you just invoke Python code, right? And there's no limit to what you can invoke. So for us, we had to make a custom parser based on Antler to achieve what we want and push down those operations. So it's like this will run on Spark SQL, and then this will run on native Spark, stuff like that.
Mm-hmm.
Eric, it reminds me kind of F strings. Think about it. It's like only SQL. Because you plug in something.
Yeah, actually, Jim Baker, who wrote, who's heavily involved in Jython, is working on a sort of enhanced F string where you can insert it into all sorts of other constructs, including SQL, HTML, things like that.
Interesting. So is it something that's coming up or came out already?
We discussed it at the last PyCon. I know he's still working on it.
Well, maybe they should talk to Kevin. Maybe they'll plug it into Fugue.
Yeah.
Sure. I'm happy to meet anyone that like you think would be like useful to would be good to meet.
Mm-hmm.
There's a question. I mean, I don't know if you had more to say, Eric. There's one question by Dave. No, but
although I haven't used Antler in years. Good to see Antler being used. I haven't used Antler in years and years.
Actually, before we move on to your question, Dave, there is something special about Fugue SQL in the sense that like SQL itself, if you think about it, is the most like scale agnostic grammar for expressing compute workflows. Your SQL code will not change if you have 1,000 rows or 100,000 rows or 10 million rows, right? So SQL is agnostic, and because of this, Fugue aims to be agnostic as well. But on the SQL side, what we find is that there's a lot of synergy with like, for example, DuckDB, which is like a local OLAP type SQL processing engine. So you can process like on top of your Parquet locally with DuckDB, and it's really fast. And then when you're ready to migrate that code over to the Spark engine, you just change the engine, and then it now runs on Spark on top of a cluster. So there's a lot of synergy. We just choose, like, we'll just run this engine locally and then this engine for distributed, right? Dave is asking a question. I have been trying to do some of my work against a remote Spark cluster running on EMR, and the challenge is getting insight into what's going on in the cluster when things don't run as expected. Wondering if anyone has a way to bring cluster diagnostics to Jupyter. So Dave, one of the things about Fugue is that we let you express your code locally in Python or Pandas, which have very good tracebacks. And then when you're ready to bring it to Spark or DAS, you just change the engine. But our guarantee is that, assuming you don't have like memory issues or stuff like that, our guarantee is that the code will work. And the reason we go this route is because when you use the Spark, when you use Spark or when you use Dask to write your code, debuggability is very, very hard. Like the tracebacks are very, very long. And that just has to do with, the engines and them using futures to represent the objects that are being used. And by using Fugue, what we can do is we can have your code debug it locally very well because the exceptions are much easier to read, native Python, Pandas. And then when you're ready, just bring it to Spark. So in that sense, there's more insight. But to your specific questions, I think Han's suggestion is good. Check the Spark UI. It's kind of hard, but that would be the best place if you already have code running.
Unless someone has a question, I have another tough question. If you can take a tough question, is it okay?
Yes, sure.
Okay.
Just have to ask you to stop the recording.
Do you want to stop the recording for that question?
No. I'm just joking. You can ask anything. I'm just joking.
Okay, so I know that there's. Think about huge data, like really big data, where you actually don't fit in memory, don't fit in nothing. You have to it's a cost, and then you have to do something like sum all the numbers and something like that. Like in a bank account, you have all those transactions, you have to sum them or whatever. So it's huge. The number of transactions huge. What happens is today you have tools that accelerate those. I heard that, for example, there are those tools that run on GPU that can run things like this over huge amounts of records. Do you plan somewhere in the future implementing some of those technologies beyond Dask and Spark?
So
I don't
number
remember the
one,
names currently, but I've seen those presentations about how GPU is used to do those things faster. Or approximately.
No. Yeah, so you're talking about Rapids and Blazing SQL and basically cuDF, the CUDA data frames. On the SQL level, there's this project there was this project called Dask SQL, which was SQL on top of Dask. So we partnered with Dask SQL for them to be one of our backends. Now, Dask SQL has since been not taken over, but is being heavily contributed to by NVIDIA. And what they're doing is that they are using the same SQL interface to run number one locally, number two on Dask, and number three on GPU data frames, right? So if they achieve, because of our nature being an abstraction layer, once they complete that work, we can just wrap over and say, okay, we're now an abstraction layer over GPU data frames as well, right?
Ooh, powerful.
Yeah. On the SQL side, on the Python side, it would require some implementation on our side. But SQL, yes, we could.
Oh my God. Okay, this is good news then. Okay, so it wasn't that tough of a question. I have to think of something tougher. Yeah, you're beating my hardest questions.
No. So it would be Fugue's goal is to be this agnostic engine agnostic layer that would then just push down your code to the underlying execution engine. So like Han mentioned, he's working on Ray. But yeah, something that Han is mentioning that's also interesting is Snowflake, right? Because when we talk about
Tell
Python
people
plus
about
SQL
Snowflake. Tell people about Snowflake.
Yeah, so for people who don't know Snowflake here, Snowflake is just a data warehouse. It you host your data there, bunch of tables, optimized for analytics. Let's just put it that way. And you would normally query Snowflake using SQL, right? So you're using SQL against your data warehouse. Now, for recently, Snowflake announced the full release of Snowpark, which is the Python interface to be able to query your data on Snowflake. So if you think about this concept of SQL plus Python, Snowflake is also within our wheelhouse and within our roadmap that we can have you define your workload in Python or you define your workload in SQL, and we'll be the ones to port it over to Snowflake. So you should be able to prototype on Pandas, and when you're ready, bring it to Snowflake rather than keep testing on Snowflake, right? Because right now you don't have a choice but to keep testing on your Snowflake warehouse or some test version of your Snowflake warehouse.
Interesting. I can see you have use cases because you're an abstraction layer, then you can actually, and you guarantee that the code will run, then you can actually do many, many things application wise. You can test things locally and then change system. And in the long run, it also allows you to change the entire infrastructure for a big company, for example, to migrate. A company is being bought over, and now you have to migrate all the code to adapt to a new environment because the buying company needs a new environment. And yeah, I can see that.
Yeah, so something that Han mentioned there is that he's also working on the Ray integration. So Ray is relatively new compared to Spark and Dask, but if Ray somehow became the predominant distributed computing engine a couple years from now, then if you use an abstraction layer, you shouldn't have to rewrite your code to port over your workflows to Ray, right?
Okay. Yeah. You just have to switch. So basically,
exactly.
So if you're working with data, then Fugue will do things for you. What about computation? Like if you're just running, well, actually you showed us a computation example of the SQL. If you need just like intensive computation, like, you know, high CPU, less data, can Fugue help?
I mean, to the extent that, like, if you're doing everything locally, our value add is not necessarily. So like, let's say you just need pandas. Can Fugue help you? We find that number one, if you use pandas for your project, then you're kind of coupled to the pandas interface, which introduces problems in itself, right? So, but I mean, like, I think Fugue really shines when you can really for distributed compute, when you need to scale out that business logic. So for Fugue's real value add is that you, as the data scientist, you can focus on whatever business logic you want to actually work on, and you don't need to worry about that execution engine specifics, right? That's where Fugue's value add is. If everything is running fine for you locally, diminishing returns, Fugue has some benefit, and I can show you what I'm talking about. And Eric, I was too quick over here to go over this portion, but remember this portion over here with type conversion, where we have different ways to express the same function. So there are a lot of times when you'll find that pandas is just very weird to express your logic, and it's a lot easier in this listic kind of structure. You can define your function like this, and we can still interpret it using the transform function, right? So there's still some benefit in that you can express your logic in much simpler ways in a lot of cases.
Okay, let me rephrase my question here. The one I asked before. What if I needed to run the same, like you had example of prediction of something. What if I needed to run it multiple times?
Like if you're yeah.
Or like 10 times over the same data. Can Fugue help me there? Like, is it something like Dask does this for me today? Like when I do my disease models, I run multiple models on the same data.
Yeah. So anytime you use some kind of multi-processing, you're going to have to copy over that data. So as long as you have enough, like even on a local machine, you can use local Dask with Fugue, right? Or you can use local Spark with Fugue on your, and then rely on, again, like what I showed in the first part of this presentation, like that kind of do-it-yourself parallelism has some limitations. Yes, it can work, but then you have to manage memory yourself, right? Whereas with using Fugue, even on local Dask, you can just like rely on Dask to perform that distribution of your job. Okay. Because Dask is multi-core, yeah.
Yeah, I got that. My question, I'll phrase it again. I don't care about the data being duplicated 100 times or 100,000 times. This is not my problem. I just want to run it on, let's say, 10,000 machine, the same thing. But let's say it's a random process. I want to generate random numbers and check out whether what's the mean of the random numbers in 100,000 machines or 1,000 machines or whatever.
We could do that. I mean, like, is your question that we are too tight to the data frame?
Sorry? No, not data. You showed the 4 quadrants about what happens if you have big data.
Oh, I understand what you're saying. So you're saying you're on the up.
Yes, I'm on that one. I need the CPU.
My CPU is limited. My memory is like at that quadrant is very hard to deal with, and in practice, you should just scale more horizontally, or you there's a lot of we've dealt with some companies. I mean, like their pipeline will take 6 hours. There's no further optimization we can do there, right? If it really takes 6 hours on Dask on Spark already, maybe there's not much there, you know? Yeah, that's a hard problem in itself.
Okay, let's leave it at this. After the recording, we'll talk more. But we have to stop somewhere. So if someone has one last pressing questions, let's come in and ask the question, please. Related to Fugue, before we stop the recording.
I
So-
want to open it to not necessarily Fugue also, but Spark, that distributed computing, scaling code in general, feel free to ask.
Okay, yes. Anything about fugue over distributed computing? Going once?
This is Glenn. I have a question. So the question is really related to comparing with a GPU-based cluster. Is there any difference if a GPU was used behind it, or does it improve it over, the performance above PySpark on GPU?
I would say, so first of all, if when we talk about GPU data frames, the assumption there, number one, do you have a cluster of GPUs, or do you just have like one machine with a GPU?
Well, if you could elaborate on both cases, because I think it helps understand.
Okay. So I will say that number one, we talked to a bunch of people who work at NVIDIA, and they're some of them, have some work related to GPU data frames, right? And for those of you who aren't less familiar, the concept of having a GPU data frame is that I have, instead of having a 4-core machine or eight-core machine, I now have thousands of cores in a machine, weaker cores, and because of that, I can more massively parallelize my operations as some very small operations, and then maybe I should see some speed up, right? So, but beyond that, there's also, when we talk about like stuff like Rapids, for example, by NVIDIA, they have packages that let you use clusters of GPUs. So like I have 10 machines, each with a GPU, and I spread my data frame across all of that, right? Now, to that question, the thing about GPUs is that, for example, if my code is already written in pandas, there are some pandas operations that don't translate well to GPU, right? And for example, like median is the most common example, right? If I have like, 10,000 rows and I have to find the median of something, what happens is that, so with the GPUs, so a machine will have a CPU and will have the GPU, and it will move all the data from CPU to GPU, massively parallelize the operations. But for anything that can't be parallelized by the GPU, it has to bump it back out to the CPU. So for an operation like median, for example, that's not parallelizable, it'll bump it back out to CPU. And then after that, it'll pump back the data into GPU and then run stuff again, right? So the main consideration there is just like there are the same principles with distributed computing in general, that you need to know kind of which operations make sense on the GPU versus the CPU. And you want to try to keep as much of your operations chained together running on the GPU before you have to pump it back out to CPU, right? Now, to the second part of your question, like how do you use you could use we don't specifically support cuDF we support Blazing SQL, which was like distributed SQL data frames. But on the Python side, we don't support like the GPU, like cluster of GPU quite yet. I would say that we don't support it on Fugue just because there's no urgency to, just because there's not a lot of people working with clusters of GPU machines. Like that's a very 1% kind of thing. So but if we had to, then we could, again, as an abstraction layer, we could extend it towards that direction, towards that direction as well, where you can prototype locally, and when you're ready, bump it back up. You use the GPU, like Rapids engine to work over like a cluster of GPU. Does that answer your question?
Yeah, I have, if you may allow me to further ask another question onto that. I have an environment where I have a Databricks environment that I'm trying to run a very intensive model that takes a long time to run on a CPU, just running on Databricks with PySpark. If I were to apply, and I am provisioning a GPU, but only a single GPU cluster. If I were to try to apply Fugue module to it, would I gain any benefit or performance for training a model? It's a prediction, so it's really like a survival model. taking categorical data, vectorizing it, and doing like a boosted decision tree and then running a model training on that. I need that to be, I need that performance increased.
So I can chime in. So that depends on like what kind of, you are talking about if training can be distributed. And then distributed training, there are two major scenarios. One is you want to use a lot of data to train one model. Another scenario is you want to train many, many models in parallel. For example, you have a very large data set, and for example, you have 500 stocks, and for each time series, for each stock, you want to train a separate model. And then that's a different type of distributed training, right? So first of all, I just want to understand which scenario fits your need.
Yeah, the use case I'm talking about is a single model with 20 years of data and a lot of categorical vector feature data on one model trying to train. And if I currently only have one Databricks cluster available, or if I used Fugue and if I had a second cluster, either GPU or GPU and CPU, would I gain a benefit?
I think again, I still need to need some more clarification of the problem. So when you feel it is slow for your current setup, are you sure it is slow on the training side or slow on the pre-processing side, where we just generating that training data for the final training? Because if, for example, if you use light GBM, even like a 10 gig or 20 gig of data, it just take a few minutes to train. It's not too heavy, but sometimes the pre-processing can take a lot of time. So I want to understand if it is the pre-processing step or just the training step is slow.
Oh, well, I think you've given me some homework to go figure out, because you could be bringing up a point that I did not understand. And now I need to go figure out how to estimate if the pre-processing is taking the time or not, because I'm running a routine that someone else wrote using the XG Boost model. It could be doing pre-processing first, and I wasn't aware of that.
Got it. Yeah. So I think by figuring out that, actually, you also you will be more mindful about your own pipeline, which is a good thing that we expect to happen. Is you're mindful like what is the pre-processing, what is the training, and how much the pre-processing takes, and how long the training takes. So ideally, for example, if let's say you have like a 20 gig of data. So if you take a lot of time for pre-processing, what you can do is you can spawn a Spark cluster without GPU, just to process the data, pre-processing the data distributedly. And then for the 20 gig of data, and then you can just start another very small cluster with powerful machine or GPU machine, and just to do the training itself. So just by doing this, you will save a lot of time, and also you will save a lot of money.
Okay, well, I have the homework then to go figure out how to split up the pre-processing and what does that consist of.
I don't know your name because it says iPhone here, but if you want to follow up, like feel free to email me. I'm going to post it in the chat.
I will. My name's Glenn. I will follow up with you.
Glenn, all right. Yeah, I'm happy to chat more about that also.
That's great.
Glenn, if I understand correctly, Fugue, then basically if you switch to it later on, you can do whatever you want. If it's possible to speed up, it'll be easier to test, because in Fugue, you just try this, try that, with this engine, with that engine. And it doesn't change your code. This is the advantage that I understand. Correct, Kevin? Correct, Han?
Yes.
Yes. we should, that is the advantage for his specific use case. Like we may be able to, if it's, for example, the inference part is not being efficient, we may find a way to just parallelize that also. But it's kind of, sometimes the overhead for distributing ends up makes the job slower. So we have to really just like, that would take some kind of specifics to work through.
Any more pressing questions from anyone? None so pressing questions related to fugue. Going once, going twice, and I don't see any other questions. So going 3 times, no more questions. Okay, Kevin, you probably explained so very well, so no one has any more questions. So at this point, I would like to thank you. So please unmute yourself, make some noise, and clap your hands. Put something in the chat. Thank Kevin.
Yeah, thank you for having us.
Nice presentation.
If anyone has any,
Thanks, Kevin.
if anyone has any questions, just please feel free to email anytime. Happy to chat with anyone. Yeah, working on Fugue full time now, so I have time to chat if anyone wants to reach out.
Okay,
Or
put your details in the chat, wherever your contact information in the chat, people will contact you. I know that some people will contact you for sure. You will be overwhelmed.
No, I don't think so. That would be a good problem.
I know from previous people who presented, but you will be overwhelmed. You'll have to pick at some point whatever you're answering. But well, hopefully you will. This will be a good thing for us. At this point, I'll stop the recording. Thank you again, Kevin. I'm going to stop the recording. Don't go away. We haven't finished yet.